The title of my presentation is Potential Corrosivity of Untreated Groundwater in the United States. This work was conducted as part of what is now being called the National Water Quality Program. Steve Moulton is our coordinator. The program that many of you are familiar with, the National Water Quality Assessment Program, is now a project within this larger structure. Gary Rowe is our chief scientist, and I'm the chief for groundwater assessments. Motivation for our work on corrosivity starts to a large extent with the occurrence of lead in drinking water in Flint, Michigan, which in turn raised questions from the public, from the press, from congressional representatives about the quality of drinking water elsewhere in the nation. Some of that attention was through the media. Here's the USA Today headline pointing out that comparable problems occur in Washington, D.C., Philadelphia, and other water systems. As is often the case when a press report comes out, it brings together a lot of data that may or may not necessarily been able to be brought together in that way. So what we'd like to do is focus a little bit more, and what we want to do today is focus on groundwater, because groundwater provides about 45% of the nation's drinking water. In particular, we'd like to focus attention on private wells. We want to focus attention on private wells because they are largely unregulated and largely unmonitored. Lead exposure in these water supplies is potentially widespread because about 44 million people rely upon private wells. Given that kind of background, the question becomes, what can the USGS do to inform the public on this issue? The USGS has data, modeling, and research capabilities to characterize source water quality. That includes both groundwater and surface water, and we can do it spatially and over time. Today we'll focus on the groundwater and the spatial component. The U.S. Geological Survey is continuing to do work on surface water and with time. The data that we can rely upon to do this work has been collected by the NAWQA project from 1991 until present, and also an extensive database collected primarily through the Cooperative Water Program. These two data sets are brought together in the USGS National Water Information System, or NWIS. Let's take a background look at how can source water quality affect the occurrence of lead in household water supplies. Previous studies have shown that source water can interact with pipes. For example, it was a Virginia study collected by Pieper and others. They looked at more than 2,100 private systems in Virginia, and they found that nearly 20% of what they call first flush water exceeded 15 micrograms per liter, the EPA action level. If one looks at how source water can affect the occurrence of lead in household water supply, one aspect to look at is mineral deposition or scaling. If minerals are deposited on the inside of the pipe, then that pipe can be protected from corrosion. There's no guarantee, but it can be protected from corrosion. Many of the indices for looking at mineral scaling or mineral deposition have to do with calcium carbonate. The conditions under which calcium carbonate precipitate are comparable to the conditions under which lead carbonate precipitate. So lead can be removed from the water or sequestered along with mineral scale. In the absence of mineral deposition or scaling, one can see corrosion. If the pipes are made of lead or there are other lead components in the system, then one can dissolve that lead if it's present. If copper is present, that can enhance the dissolution of lead because it sets up electrochemical potential. So for example, if one has copper pipes with lead solder, the presence of lead and copper can set up an electrochemical cell. So furthering on this question of how can source water affect the occurrence of lead in household water supply, the USGS has mapped two indicators of corrosivity at about 27,000 locations shown in green on this map. The two indicators are the Langelier Saturation Index, or LSI, and the potential to promote galvanic corrosion. The Langelier Saturation Index is a measure of calcium carbonate saturation and therefore a measure of the potential to deposit scale. The potential to promote galvanic corrosion is based on the chloride to sulfate mass ratio, or CSMR, and alkalinity. The LSI has long been used since the 1930s. The use of the chloride to sulfate mass ratio and alkalinity was outlined in a paper by Nguyen and others in 2010, and we have recast that work for this purpose. Important to note that corrosivity of source water is one of many factors that can affect the occurrence of lead in household water supply. Certainly one needs lead in the pipes, whether the water is filtered, temperature changes that can occur in the system, pressure changes that can occur in the system are all factors as well. But corrosivity of source water, particularly if that source water is untreated, is an important factor. Let's take a look at the LSI for groundwater samples collected by the USGS from 1991 to 2000. The orange circles show sites where the LSI is more negative than negative 0.5. We've denoted these as potentially corrosive. Shown in gray squares are groundwater sites where the LSI is between negative 0.5 and positive 0.5. Values in that range can be considered indeterminate. Other factors contribute to whether scaling can occur. So for this purpose, we've called that indeterminate. Shown in blue X's are sites where the LSI is greater than positive 0.5. These are conditions under which scale is more likely to occur. One simply looks at this map. There are 22,000 locations. 32% of the sites are coded corrosive, 63% indeterminate, and 5% scale forming. These data are shared via a website, and this presentation will be made available to you, and you can head towards that. Let's take an alternative look at this data. What we'll do is, for each state, we'll simply collect up the samples for that state, and we will present it as pie charts. In addition, for each state, we'll calculate the average LSI and then code the state based upon the average for the values in that state. Well, the human eye is not always the best integrator, so this helps to show that. So again, we have a pie chart. The orange slice is the proportion of sites in a state that are potentially corrosive. The slice in gray are sites that are likely indeterminate. The slice in blue are sites where it is likely scaling. A state is color-coded salmon if the average value for that state is more negative than 0.5. Right away, what we see is states coded as potentially corrosive at a statewide scale in the Northeast, Mid-Atlantic, the Southeast, Pacific Northwest, and Hawaii. Again, this map is shared via a website. Let's take a closer look at the Northeast to get a sense of how things can vary within a state. So again, the Northeast, we see a preponderance of orange in these pie charts. We see that the states are salmon-colored. So for example, if we look at the state of Massachusetts, here's the Connecticut River. It forms the boundary between Vermont and New Hampshire. You can see the little nick into Connecticut. To the east of the Connecticut River, we see a preponderance of sites coded as potentially corrosive. To the west of the Connecticut River, we begin to see additional sites that are either indeterminate or potentially scaling. In addition, we've highlighted sites that are more negative than negative 5.0. The orange circles are for sites more negative than 0.5. The red fill are for sites more negative than 5.0. I'm calling your attention to eastern Massachusetts. We don't have very many samples on the Cape, but if one looks at Long Island, one begins to see a relatively large number of sites that are very negative on this LSI scale. So let's look at the southern portion of the Northeast. We had looked at New York northeastward. Now we can look at Pennsylvania southward. This time I'll call your attention to New Jersey. You can see there's a rough approximate line here. To northwest of that line, a large number of sites are corrosive and indeterminate. As we head southeastward of that line, we see sites that are also corrosive. We see a few sites indeterminate, but we begin to see a preponderance of sites in which the negative values are more than negative 0.5. Let's take a closer look at New Jersey. Again, this time we'll put the geology up beneath it. So here we have the outline of the state. Again, the orange open symbols are sites coded as potentially corrosive. The gray squares, indeterminate. The blue X's, of which there are very few, are scaling. The red fill are for sites more negative than 5.0. Let's take a look at the deposits. The cross-hatchered area are glacial deposits. Underlying the glacial deposits on Long Island are the North Atlantic coastal plain, shown here in beige. It extends up through here. Shown in this blue color are early Mesozoic basins, And we won't focus too much on the rest of these provinces. So here we see a contact between the early Mesozoic basins, the North Atlantic coastal plain, and we can see quite clearly that the most negative values for LSI, the groundwater samples that have the highest potential for corrosivity, are largely associated with the coastal plain, the North Atlantic coastal plain in this case. So we presented a map at a national scale. If one looks more closely at the states, one can see more clearly the relationship between the subsurface materials and the groundwater that comes from those materials. We've looked at the LSI. That is an indicator of the extent to which corrosion might occur because pipes in essence aren't lined and or because lead's not being sequestered. The potential to promote galvanic corrosion results from when lead and copper are both present in the system. Electrochemical potential exists because those two metals have different chemical potential. Lead is dissolved in the presence of electrolytes. Copper is precipitated. Shown in brown are groundwater sites that have a high potential to promote galvanic corrosion. Shown in blue-green or Miami dolphin green are sites that are moderate, and shown in X are values that are low. On the LSI, we had three classes. The middle class was indeterminate. We could neither say it was scaling, nor could we say it was corrosive. On the PPGC, this moderate corrosivity is potentially corrosive water, so it's not exactly the same classification system that we saw on the previous slide. We have 27,000 locations at which we can make a determination for PPGC. 8% are high, 67% are moderate, 26% are low. Again, this 67% moderate doesn't mean there isn't a potential to promote corrosivity. It just means that it's not as high. If we look at these highest locations, they are in the Northeast, the Mid-Atlantic, the Southeast. We see it in the Pacific Northwest. We see it in Hawaii. For those of you from California, you can see values in the Sierra Nevada. You can see values in the Central Valley. Again, let's take that data and aggregate it up at a state scale. The classification for PPGC was qualitative. It was low, moderate, high, whereas for LSI, it was numeric. More negative than negative 0.5, between negative 0.5 and positive 0.5, and greater than 0.5. So our statewide classifications are based upon proportions rather than averages. Let's begin with our pie charts. Shown in the blue color are sites that are low. Shown in the blue-green color are sites that are moderate. Shown in brown are sites that are high. Each of these is a proportion. So, for example, for New York State, you can see a large proportion of sites in the moderate category. If we look at the sites in a state, if more than half of the sites in that state are low, we characterize the state as low. There are only 6 such states, all located in the high plains and the Rocky Mountains. Other than these 6 states, the remaining states are less than 50% low. Alternatively stated, more than half the sites are either moderate or high. So we're going to take a look at those states and ask the question, are more than 1/4 of the sites high or not? So shown in brown are states where more than 25% of the sites in a state are high, less than half the sites are low, otherwise we code moderate. So again, if you look at a moderate state, you can see that there are no high sites in this particular state, or if there are, it's a very thin slice. It's not showing up at this scale. You know, what is that, about 2/3, not quite 3/4 are in the moderate category, about 1/4 to 1/3 are in the low category. So the state classified out as moderate. If we focus our attention for a moment on the high states, we see they're in the Northeast. We see that in the Southeast. We saw a number of sites coded as having a high PPGC, but at a statewide scale, they don't shift those proportions. Similarly for Hawaii. So the PPGC is mapping out as high for the Northeast and the Southeast. Again, let's take a closer look at the Northeast just to see how things vary within a state. Again, calling your attention, for example, to Massachusetts. Again, here's the Connecticut River. To the east, we see a relatively large number or a large proportion of the sites coating out as high, a few sites coating out as moderate. If we look to the west of the Connecticut River, we see a preponderance of sites in the moderate category. We see some sites coating out as low. We're not seeing sites really coating out as high. So again, this reflects the materials from which the groundwater samples are being collected. These maps for PPGC, these data for PPGC are all available for download. Let's shift our attention to the south, and again, we'll focus on New Jersey, shown through here. And again, we have this relatively nearly straight contact. To the northwest, a preponderance of sites coded out as moderate, some sites as high, a small number as low. As you head to the southeast of that line, the proportion high goes up. And again, we'll put up the underlying hydrogeologic units. The beige colors the North Atlantic coastal plain. The deeper blue are the early Mesozoic basins, the crosshatch glacial deposits overlying other deposits. So again, we have this contact, and quite clearly you can see that those sites coding out as having a high PPGC largely associated with the North Atlantic coastal plain. So when we move upward towards Long Island, we move downward towards Delaware and southward, we see a similar relationship. The North Atlantic coastal plain has groundwater that is potentially corrosive under this metric. So we looked at the LSI, we looked at the PPGC. Let's try to bring these results together, even though they are different indicators. The Langelier Saturation Index, we have potentially corrosive, indeterminate, and scaling. At a statewide scale, none of the states classified as indeterminate, nor as, none of the states classified out as low. They either classified out as moderate or as high. If we look under the PPGC, the potential to promote galvanic corrosion, our states classified out as under all three. And then when we look at these combinations, there are 9 possible combinations, 3 on LSI, 3 on PPGC. And when we see potentially corrosive under LSI, we see that it could either be high PPGC or moderate, but we don't get the case that we have low PPGC at a state scale and potentially corrosive for LSI. When we look at indeterminate, we get moderate and low. We didn't get any scaling, so none of it classifies out as here. So for the 9 potential combinations, only 4 show up. Let's take a closer look. Indeterminate is indeterminate. We can either say that it's high or low. So if it's moderate for PPGC, we'll just inherit that descriptor, moderate. If it's low for PPGC and indeterminate, we'll inherit that low. Moving up from moderate, it's moderate PPGC, it's potentially corrosive, we'll call it high. If it's high for PPGC and potentially corrosive for LSI, we'll code it out as very high. So 4 categories, that's the logic chain. So these are our 50 states plus the District of Columbia coded out as one of those 4 categories. These are the 6 states that were low for PPGC. They were indeterminate for LSI. They code out as low prevalence. Shown in the darker shade of orange, these were states classified out as potentially corrosive under LSI and having a high potential to provoke galvanic corrosion. So we see those coded out as darker colors, and then the other states shown accordingly. Let's take a look at how many domestic well users, or what the population is dependent on private wells. These deeper orange states, very high prevalence for potentially corrosive groundwater. There are 8 million people dependent on private wells. If we look at the next category, high prevalence, 16 million people. If we look at these green states, the largest number of states in the country, there are about 18 million people dependent on private wells in those states. So there are 24 million people in the high prevalence and very high prevalence, 18 million in the moderate. We look at the 6 states, 1 million people in those 6 states dependent on private wells. So let's summarize, and then we can take some questions. Corrosive source water, if untreated, can dissolve lead and other metals from pipes and other components in water distribution systems. The USGS has prepared maps of the potential corrosivity of untreated groundwater in the United States. The Langelier Saturation Index is an indicator of calcite saturation. That's one of our indicators. The potential to promote galvanic corrosion is based on the chloride to sulfate mass ratio and alkalinity. That's the second of our indicators. We combine those two into a combined index and have one map to show that. Potentially corrosive groundwater occurs in all 50 states. 25 states were classified as high or very high prevalence. 24 million people depend on private wells in these states. 19 states were classified as moderate prevalence. 18 million people depend on private wells in these states. These results have been published in a scientific investigations report, several data releases, and we have a website. If you have questions, these are our contact numbers. Steve Moulton, again, is our program coordinator for the National Water Quality Program. Gary Rowe is our chief scientist for the NAWQA project. My name is Ken Belitz. I am the groundwater lead for assessing groundwater for NAWQA. We have a website. If during the questions you'd like to take a look at the website, again, here is that link